Hello, my name is Pierce and I'm one of the math tutors here at the DLASC. And today I'm going to be working a differential equations problem, but also be kind of deriving the integrating factor technique. So the integrating factor technique is one that you'll learn shortly into the class that essentially says if I have some differential equation taking the form a of x times y prime plus b of x times y equal to, let's call it r of x. The way we would have done this is broken up our y prime as dy dx, tried to separate the equation in such a way that we had dy on the same side as the y's and the dx as the same side as these functions. But here we're going to assume that there is some, what I'll call an integrating factor I of x, that is going to be equal to e to the integral of q of x. And obviously in this problem, I don't have a q of x, so let's go ahead and get rid of this a of x here that's stuck onto our y prime such that we make the equation monic, meaning that the y prime doesn't have a coefficient. This b of x divided by a of x, I'm going to call p of x, y equal to q of x. Go ahead and redefine this such that it is p of x. In this scenario, you can see that the integral of this p of x is going to be my I of x. So what we want to do is multiply this entire equation by I of x such that x, y is equal to I of x, q of x. This is what we're left with. If you recall the derivative of two functions being multiplied together, in this case they're dependent on x, is the product rule. And the way we wrote the product rule was f prime x plus g of x f prime g of x plus f of x g prime of x. And if you look at our equation, that's exactly what we've done here, where our y in this case is our f prime, our I of x is that function g, plus I of x times p of x is really our g prime. Our y is our f. And why is it our g prime? Well, remember, we defined I of x as e to the power of the integral of this function p of x right here. So what we can do is integrate both sides such that the integral of the derivative with respect to x of y times I of x with respect to x is equal to the integral of I of x times q of x with respect to x. And from here, we can go directly to y times that function g, in our case I of x, is equal to the integral of I of x, q of x with respect to x. From here, of course, we would divide this I of x off, meaning the general solution for our differential equation is going to be 1 over I of x times whatever this integral comes out to be. In my next video, I'll work an example with this so you can see how this technique is extremely useful for evaluating a lot of the equations you're going to come across. The only tricky part is that whatever this integral here, I of x, q of x b is, you'll have to use some of the techniques you learned in Calculus 2. So integration by parts, substitution, rarely trigonometric substitution, but the big ones typically are going to be your integration by part rules, and occasionally you'll have to do a trig sub.